In section 3.1, we're going to look at lots of shortcut rules that we can use to find the algebraic derivative, which is probably going to be much quicker than using the long limit definition that we saw in section 2.5. So hopefully we'll arrive at the same answer we would have with the limit definition, but these shortcuts are just a little bit quicker. So the first shortcut we have is if we have a constant function. So let's say here f of x is some number, let's say 5. Okay, well, if we have a constant function, let's see if we could graph what that might look like. I have 5 here, and if we're a constant, that is just a horizontal line right here. So if I want to know how this constant is changing, well, a constant doesn't change. So its derivative is always 0. Okay, so the derivative of any constant, if there's not a variable in the term, its derivative is going to be 0. Now, some of the tricky ones, we might see something like f of x is e squared. Well, do you see e is just a number and you square it, that's all number, so its derivative is going to be 0. Or we might see one like g of x equals 2 pi. Well, again, even though pi is not a traditional number, do you see that because there is no variable there, its derivative is going to be 0. Right, the second one we will use quite often is the simple power rule. So if you have a variable to a power, well, instead of using that long limit definition and expanding that out with the x plus h, what we can do is take the power, let's say it's x to the n here. Well, what we might do is take this power, I'm going to bring this down as a constant. And then instead of having n up here, now I'm going to have 1 less. Okay, and we'll see an example in a couple seconds, but just really quickly here, let's say I had x to the 7th. We'll call this f of x. Its derivative then, f prime of x, I'm going to take that 7 and bring it down, so I get 7x, right? And then I'm going to reduce that power by 1, it is now 6. Right, and then the next shortcut is if we are multiplying by a constant. So we have a function times a constant. Well, that constant can just come along for the ride, and it's just the constant times the derivative. Now let's make sure we understand the difference between these two. Here I'm multiplying a constant by a function. So I'm going to have some variable in there. Whereas in my constant rule up here, this constant is all by itself. There is no variable. So if I'm multiplying a function by a constant, that constant can tag along and I can just multiply it by the derivative I find. And the last shortcut rule that we have here is if you're taking the derivative of the sum of two functions, you can just take their derivative separately. Or you can take the derivative of each term separately. That's what that one says. All right, now we're going to learn some other rules after spring break, but these four will help us with test 2 and also checking our answers on those long limit definition problems. All right, so the first one we have here, remember all of these use that constant rule. So if I have a constant its derivative is 0. So if y, notice that there is no variable over here. So because there's no variable over here, its derivative is just 0. Okay, and here's a tricky one. F of x is pi. Well, pi is just a number, right? 3.14159 and so forth. So its derivative is 0. So if my function here is the speed of a car, and this car has its cruise control set at 65 miles an hour. The derivative here, if I want to know, well, how is the speed of the car changing? Well, it's not changing, right? Because my cruise control is on. So it's just 0. Okay. Now, next we want to use that simple power rule. So if I have a variable to a number, so x squared here, and I want to take its derivative, I don't want to have to do all that x plus h and FOIL stuff out. So what I'm going to do here, my shortcut, I'm going to take this 2, bring it down, and then reduce it by 1. So this is going to be 2x to the first, which is the same as just 2x. Okay, if I have x to the fifth, I'm going to bring that 5 down as a multiplier, x, and my new power is 4. Okay, now these rules that we have up here at the top, these are not derivative rules. This is these are our algebra review rules. But the problem is, if we have an equation that looks like x to a power, this rule is very handy. But we might have to remember some of our algebra rules to get our functions to look something like x to a power. So for example, if we had the square root of x right here, well, what we would like that to look like is x to some power, okay? Now, if you remember, the nth root of x is the same as x to the 1 over n, so that in this case, if it was the square root, this would be x to the 1/2, okay? Now, I did not do any calculus there. I was just rewriting it so that now my calculus step will be easier, okay? So let's say I had the, for here, I had something that looked like the third root of x squared, okay? Well, I want to rewrite that, right? So if this is to the power 1/3, and 1/3 times 2, this would give me x to the 2/3. Okay, and once again, I haven't done any calculus yet. I've just rewritten this so that I can now use some of those calculus rules more easily. Okay, and then another rule that we might see, let's say I have 1 over x to the 5th. Okay, well, we can't just take the derivative down in the denominator. Anytime we see a quotient in this course, we're going to have to rewrite it. So I'm just going to rewrite this as x to the -5. Okay, and again, that was just an algebra step. Now I'm ready to tackle this problem using my simple power rule. All right, so after that quick little algebra review, if I have the square root of x, I can first rewrite that as x to the 1/2. Okay, and again, on the left-hand side, I have not yet taken the derivative. Now that I have it look like a variable to a power, I can take the derivative. So I'm going to bring that power down, x, right? And now my new power is going to be 1 less. So if I take 1/2 minus 1, I get -1/2. Okay, And for the online homework, you do not need to simplify. For my test, you do not need to simplify. If this was a multiple choice question and you were trying to find, you didn't see this listed here, you could possibly look, let's say I'm going to bring that x back down into the denominator to get rid of that negative power. So it might look like x to the 1/2 or 1 over 2 root x. Okay, all three of these answers are the same. All three are correct. Okay, so if I had t, the third root of t, I can do my algebra step and rewrite that as t to the 1/3. Now I'm ready to take the derivative. I bring my 1/3 down. T, right? Then I take 1/3 minus 1, and I get negative 2/3. Okay, this is completely correct. You can stop right there if it's a free response question or if you're doing your online homework. You do not have to simplify. But if this was a multiple choice question, you might also see this written as the third root of p squared. And again, this is just an algebra step that is not necessary. Okay, if I want to take the derivative of 1 over t squared, first I can rewrite this as t to the negative 2. Okay, now I'm ready to take the derivative. Now I'm going to call this s prime of t. I'm going to bring my negative 2 down. T to the negative 3, because I subtracted 1 from that power, which is equivalent to negative 2 over t to the 3rd. All right, 1 over r would be r to the negative 1. So if I want to do that, take that derivative, let's call this s prime of r. I'm going to bring down my negative 1, r to the negative 2. Okay, which is equivalent to negative 1 over r squared. Right, now here I don't see a power. So you could think of this as x to the first power. Okay, that might help you because then you have something to bring down. So f prime of x would be, bring down my 1, x, and my new power, 1 minus 1 is 0. Now, do you remember anything to the 0 power is just 1? Which is just 1. Now that might make sense to you if you think of x as being linear, right? F of x is just x, so what was the slope here? Well, the slope is just 1, which is what we found over here as the average rate of change, which happens to be our instantaneous rate of change here because it has constant change. All right, so for t of x, I'm going to rewrite this as x to the negative 1/2. So that was my algebra step. Now I'm ready to take its derivative, t prime of x. I'm going to bring down the negative 1/2 x. And if I subtract 1 from that, I get negative 3/2. Okay, now it's not necessary, but this is equivalent to, if I bring that x negative power, I bring the x back down into the denominator, and then this becomes the square root of x to the 3rd. All right, now this one here, we're going to first do our algebra step and rewrite this as x to the negative 2/3. Okay, so it's negative because I had to bring it out of the denominator, and then the 2 here comes from my exponent there, and then remember the third root is a power 1/3. All right, now I'm ready to take the derivative. All right, so I'm going to bring down my 2/3 x. All right, now I'm going to subtract 1 from that. So negative 2/3 minus 1 would be negative 5/3. Okay, and if you wanted, you could simplify this a little bit, but it is not necessary. I'm going to take my x, bring it back down into the denominator, and I get the third root of x to the 5th. All right, next we have our constant multiplier rule. Now this is different from the first constant rule where the derivative of a constant is 0, because now I'm taking this constant and I'm multiplying it by a function. So here we have 5x to the 3rd. So my constant's just 5, okay, and then my function is x to the 3rd. Okay, so when I take the derivative, the 5 could just tag along. And then I'm going to do the derivative of x to the 3rd would be 3x squared. Okay, and you're not required to simplify, but if you wanted, that is 15x squared. Okay, now here I'm going to have to rewrite this little. So I'm going to rewrite this as 1/2 x to the negative 5. Okay, in this case, my constant is the half, and my function is x to the negative 5. So when I take the derivative here, let's call this j prime of x. The 1/2 just comes along for the ride. And then when I take the derivative of x to the negative 5, I get negative 5 x to the negative 6. Okay, and if you wanted to simplify this a little, I can combine those two constants as negative 5/2 x to the negative 6. All right, and then our last rule here was that we could take the derivative of each term separately. So if I wanted to find p prime of x, okay, I can just do this term by term. So let's start with this first term right here. Well, the 5 tags along. I bring down the 3's. So 5 times 3 gives me 15x squared. Okay, now I'm ready to move to this next term right here. I'm going to bring down that 2, and the negative 3.5 tags along. So 2 times negative 3.5 is negative 7x, and my power previously was 2. I subtract that by 1, I get to the first. All right, and then for my next term, the 9 tags along, and then we get x. Remember, we could think of this as to the first. So if I bring down that 1, I get 9 times 1 is 1, x to the 0 power, which is just 1. And then my last term here, there is no x there. So minus 6 pi squared is just a constant, so its derivative is 0. All right, so let's see if we can clean this up a little bit. We have 15x squared minus 7x plus x to the 0 is just 1, 9. right, so those are our shortcut rules. Now let's look at one that's a little tougher. Now remember, in this course, if we see a quotient, we're going to need to rewrite that quotient. Now it might not be obvious how I could rewrite this, so let me do kind of a little arithmetic review here. So let's say I had 1/5 plus 3/5 plus 2/5. All right, well, what would I do here? I would already have a common denominator of 5, so then I would just add those. 1 plus 3 plus 2 and get 5/5. All right, now what we want to do here is go backwards. I already have that common denominator of 2x. So what I'm going to do, instead, I'm going to go from this piece right here, I'm going to go back to there. So I'm going to first rewrite this as 3x squared over 2x minus 4x over 2x plus 8 over 2x. All right, now this should be much easier to work with because some stuff is going to cancel out. I've got x squared over x. Well, one of those x's is going to cancel, so I am left with 3/2 x. Right, now I have an x in the numerator and an x in the denominator, so those are going to cancel, and then -4/2 is -2. All right, then I can simplify 8/2 is 4. Because that x is in the denominator, I'm going to bring it up, and its power is -1. So that was a lot of algebra there, but now it's in a form that is easy to use that simple power rule. So I'm going to take its derivative now. Now, I hope everyone understands that everything I just did on the left-hand side is algebra. All right. Now, over on this side, I'm going to do my calculus. All right, so you can think of this as x to the 1, or just think of this as a linear term. So its derivative is just going to be 3/2. But my constant tags along, right? And then the derivative of x to the first would be 1x to the 0, which we've already seen a couple times. This piece is just 1. Okay, now my next term over here, the derivative of -2, there's no x in that term, so it's 0. Right, now my next term, I'm going to bring down that -1. -1 times 4 is -4. X to the -2. All right, so if we clean this up again, we just get 3/2 minus 4 x to the -2, or you might write that as 3/2 minus 4 over x squared, either one. All right, so here we have a function. We have a cubic function that tells us the number of million people age 65 or older X years after 2000. So my input is how many years after 2000, and the output is how many million Americans are over the age of 65. So first question, we want to know, what is the projected number of folks 65 or older in 2030? All right, so this value right here is an input of, this is going to be an input value of 30 years after 2000. what I want to do is evaluate my function. All right, so this is a test 1 question. So I'm going to go to my graph menu here. Delete this old stuff and enter my equation. All right, so this is an evaluate problem. So I'm going to go to my run menu and R's for variables. I want my graph variables. Y1 is where I save this, and we're going to evaluate this at 30. So I got here 70.87. And my units here are million people. All right, now in the second part of this question, it asks me how quickly is the projected number of folks changing in 2030. So what this is asking me for is not the function value. What I'm looking for here is the derivative at 30. All right, now we've already seen a number of ways to estimate the numeric derivative. Because does everyone understand I'm not looking for an algebraic equation here, I'm looking for a number. Now the calculator can absolutely help you with this one. So if I want to find the new numeric derivative, I'm going to go options. Okay, I want my calculus menu, and then there is DDX. Okay, now remember, if you have the black and white calculator as opposed to this color simulator I have here, yours might look slightly different, and your inputs would be, well, where did I save my equation? I saved that equation in Y1, and then I need to tell it where to take the derivative, which is at 30. Okay, so here I get an answer of 1.509. All right, and now I need some units. So my units here would be million people per, what are my input? My input is X year. So this is million people per year. All right. Now, hopefully, if we took the derivative by hand and plugged in 30, we would get the same answer. So let's see if we can do it that way and hopefully confirm what the calculator has told us. So first, I'm going to find the algebraic derivative that will work anywhere on that function. Then I'm going to plug in 30. All right, so the first thing I need to do is take 0.00082 and multiply it by that exponent of 3. Okay, now if you're doing this in your calculator, it probably gave that to you in scientific notation. If you did it in your head, you see that this is negative 0.00246. All right, now let me show you what it might look like if I did it in the calculator. If I said negative 0.00082 times 3, you see how it gave me that result in scientific notation. Okay, my power before was 3, so my new power is now 2. Okay, then I'm going to take 0.059 and multiply that by my exponent of 2, and I get 0.118. My power before is 2, so my power now is 1. Okay, then next I get 0.0183 tags along, and we've done this a couple times, but the derivative of x is just x to the 0, which is 1. And lastly, this last piece is a constant, so its derivative is 0. All right, now I want to plug in 30 here, and hopefully we get the same answer we got before. So I'm going to get negative 0.00246 times 30 squared plus 0.118 times 30 plus 0.183. All right, and hopefully that's going to turn out to give us the same result that we found when we had the calculator do the derivative. Negative 0.00246 times 30 squared plus 0.118 times 30 plus 0.183. And yes, we did get the same answer, 1.509. As before, our units are million people per year. All right, great. Now we want to calculate the percent rate of change. Okay, so we've done this a couple times here. What I'm going to need is I'm going to need the derivative at 30 over the function value at 30 times 100%. Right, we just found the function value on the previous slide, 70.87. All right, so I'm going to take 70.87 as my function value. Then we just found the derivative twice to be 1.509. Then we're going to multiply that by 100. Okay, so 1.509 divided by 70.87 times 100 gives me 2.129. And my units here are percent per input, which in my input this case is years. Now, I don't think we had to worry about rounding error here because both our function value and our derivative turned out nicely. But if you wanted to do this all in one line without having to worry about any rounding error, I can go find my derivative with option calc ddx. I have my equation saved in y1 evaluated at 30. So there's my numerator, which is the derivative, divided by. Now my denominator is the function value at 30. y1 evaluated at 30. And then I need to multiply that by 100 to change it to a percent. And we get the same answer that we just got. All right, so I want to do a couple more examples of finding the derivative here. Now, now you'll probably notice that I skipped quite a bit in this video. I'm all the way on example 8 here. I'm going to come back and get the rest of this content after spring break. All right, but this is enough to get us through test 2. So if I want to find the derivative of y, maybe I call this dy dx. But I'm just assuming that that input variable is x there. All right, so I see no x on the side, so that's a constant, so its derivative is 0. Okay, I want to find the derivative of f of x equals x to the 5th. I'm going to take that power, bring it down, 5. X, and my new power is 1 less, which is 4. Okay, now this is a tricky one because this is just a number, even though it doesn't look like a number. So its derivative, I'm going to bring down that number, 2 pi, x, and the new power is 1 less, so I might write that 2 pi minus 1. All right, so here if I want to find the derivative of this one, I'm going to bring down my 2. My constant tags along, so negative 0.5 times 2 is negative 1. X, and then my power before was 2. I reduced that power by 1. It is negative 1 x to the 1st, which is just negative x. Okay, in this next one, I'm going to take the derivative of each term separately. So the first term is going to bring down my 3. 5 times 3 is 15. X, and then my new power is 2. 3 tags along, I bring down my 2. 3 times 2 gives me 6. X, my new power is 1. And then minus the 2 tags along, the derivative of x is just 1. And then lastly, the derivative of this constant right here is going to be 0. All right, now this is another one of my quotient problems that I'm going to have to rewrite. So this is just my algebra step. I'm going to rewrite this as negative 9 x to the negative 2. Now I'm going to take the derivative of that, g prime of x. I've got a negative 9 that tags along. I bring down my negative 2. So negative 9 times negative 2 gives me positive 18 x. And now I'm going to reduce that power by 1. It was negative 2, so now it's negative 3. All right, now this is one where I'm going to have to clean up as well because I'm going to get rid of that quotient. So I'm going to rewrite this as 3x squared over x plus 1 over x. Okay, now let's see here. I have x squared over x, so one of these up here is going to cancel with that one, so that term is just 3x. Okay, so I might write this as 3x plus, now I want to bring this up out of the denominator, so I can think of that power as 1 over x to the 1st, so this has become x to the negative 1. All right, so everything I did over there was just to rewrite it. Now I'm ready to take the derivative. All right, the derivative of 3x is just 3, because the 3 tags along, and the derivative of x is 1. Now I'm going to bring down that negative 1. X, and my new power is negative 2. All right, so we can simplify that a bit. We get 3 minus x to the negative